This physics lab, I analyzed the effect of gravity and drag force on an object through a tracker and then also through a computational model and compared the two. For my object, I decided to drop a highlighter from rest and find the model position versus time through a tracker, and then I also computed graphs that took into account the object with the force of gravity and then also with the force of gravity and a drag force, and then compared all three graphs to one another. I predicted that the graph with the gravity and drag force would affect the observed graph versus the computer graph, which would lead to differences in shape. For my overall results, I found that when the gravity and drag force was taken into account, the model for the position versus time matched that of the observed very closely, which is shown in the graph in the conclusion. There were several physics principles used in this experiment. First was Newton's second law. We found that we know that the force is equal to mass times acceleration, and then we were able to rewrite this to know that acceleration is equal to the net force over mass. I also used the idea that delta V over delta T is equal to F net over mass, and then also in order to compute things like the final velocity, I used that the final velocity is equal to the initial velocity plus F net over m times delta T. Another concept that we used specifically in this experiment was that of weight over n gravity. We know that force is equal to negative mass times gravity, and that gravity is always the constant of 9.8 meters per second squared. For this experiment, we also had to take into account things like drag force, which is equal to negative b times the magnitude of velocity squared times the norm of the velocity. This is going to be incorporated into our code later. First, I used this video and inputted it into Tracker in order to track the model position versus time for when I dropped the highlighter. This is the graph that I ended up getting, and you can see that it's a quadratic graph, as in it starts off up here and then ends up going downwards, which makes sense because the object is starting off at a high position and then eventually goes down as well. And this is the graph that we're going to later compare to our computational graphs. The next step was to find the computational model, which only included the effect of gravity. So some changes that I made to our original code was that I inputted the ball's mass, which I found to be 0.011 kilograms. I set the position and velocity vectors equal to 0 because the initial position and the initial velocity are equal to 0. Delta t is going to be 0.001 because we want delta t to be small so that it's more accurate. The gravity is equal to 9.8, which is a constant. J hat would be the vector of 0, 1, 0 because we are only looking at the position, which is in the y direction. B in this case is going to be 0 for now. W, which is the weight, is equal to negative mass of the ball times j hat. And in this case, F net is only going to be W because we're not taking into account the drag force yet. The velocity and position formulas are equal to what we originally said. The velocity and position update formulas are equal to within the physics principle slide. And then we have things like the arrow scale, which is also going to be constant. And so once we plugged all this stuff into the code, this is the graph that I ended up getting. And even though it might be close to the graph of the observed model, it's not as accurate. So when we found the computational model that included the effect of the gravity and the drag, we had to make a few additional changes. So we had to find the specific b value, which is found by matching the computed end position to that of the observed end position. We also had to take into account drag force here, which I inputted. So it's negative b times the magnitude squared of the velocity times the norm of the velocity, and then the F net would be the weight plus the drag force. Then here we had to incorporate the drag force and weight into the arrows and the arrow scale. And this is the graph that we ended up getting for including the effect of gravity and drag and the drag force. And so in the conclusion, you can see the comparison of all three graphs and see that the observed graph and the graph with the model and with the gravity and drag force are very, very similar. They're almost the same. You can't really even tell the difference. And then the graph with just the gravity is a little bit off, so it's not quite as accurate. So we did see that there was a difference in the graphs because the realistic drag force and gravity are taken into account in the observed model, whereas the constant might not have been exact in the computational model. And in order to answer the questions, we found that the terminal velocity is when there's a net force of 0 because the force of the drag and the force of the gravity kind of cancel out and are equal, which leads to a constant velocity because the acceleration ends up being 0. So we can see that the terminal velocity is shown by the computer drag force and the gravity graph, since at some point the object has to stop accelerating and fall at a constant speed. And in order to answer the what if question, even if the object was thrown down at some initial velocity that wasn't 0, the magnitudes of the velocity would still be equal, but it would just slow down to reach the terminal velocity rather than speeding up. So that would be the only difference. But yeah, overall, this graph really encompasses the concluding results of this experiment.